Alrighty, welcome Flipped Physics to another lecture where we are going to be continuing our conversation of electromagnetism today. We're moving into the second part of chapter 22. We're going to be doing chapter 22B and a little bit of C. If you read the book and then hear the lecture, you will discover that I have skipped over several mathy bits for you. Just thinking about the long-term applicability of this to your continued education. We're going to focus more on concepts in this portion than on a lot of the math. I will show you one equation, but it's more conceptual for you today. So you're welcome. Moving on into chapter 22B and C. This section begins with a conversation of the difference between AC and DC current and power and how it's generated. This is a review for you from physical science many moons ago. And also we've already talked a little bit about AC versus DC power in earlier parts of this year. So an AC current, just as a review, AC current is a push and pull of electrical potential. Electrons are moving one direction down a wire, then they back up, and then they go that way again, then they back up. So the electrons never actually get very far. They're just kind of oscillating back and forth, and it's that movement of charge that electrical devices can use to do work. So the AC current is a push and pull, push and pull, push and pull, push and pull, as opposed to DC current, which is more of a flow, where the electrons are always going in one direction, going from one place to the other. Okay, to generate AC power is a lot easier to generate than DC power. You just spin your wires in the presence of an electric field, and as one part of the wire comes near the positive pole of the magnet, electrons will behave in one direction, will be moved in one direction. As that part of the wire then goes around to the south pole of the magnet, the electrons will move in the opposite direction. So you get that push-pull, push-pull, push-pull as the wire spins in the presence of a magnetic field. Okay, pretty simple. DC generators are the same thing, only they've snuck in this component called a split-ringed commuter. And what that does is it allows only one side of the wire to be attached to one side of the circuit at a time. So the part of the loop going by the north pole will always be connected to one wire of the circuit. And then when that part of the wire is going by the south pole, it's no longer attached to that same part of the circuit, it's attached to the other. So it will push on one side and then pull on the other, and then push on one side and then pull on the other, and that causes the electrons to always flow in the same direction. Okay, let me show you some pictures of that. But first, these are symbols you should know. As you are going to be familiar with reading electrical diagrams, and reading electrical diagrams is going to become more and more a part of your physics experience in the next couple of chapters, you need to be familiar with what these schematics and diagrams mean. So if you see this symbol with a plus and a minus in a circle, this is either a battery or a DC generator or a DC power source. It's direct current. It always is positive on one side and negative on the other. Versus this is an AC power source, right? And so we use the little swooshy symbol because the current is changing all the time. So this helps us think about change. It also looks like rotation going on, and that rotation helps us remember the AC generator, which is always pushing and then pulling and then pushing and then pulling as those parts turn around. Let me show you some pictures to help you understand this a little bit better. Here we have a north and south pole of a magnet, and obviously you know from your discussion of magnetism that this is not a north monopole and a south monopole. This would just be the north part of a magnet and the south pole of a magnet, and maybe it's the same magnet, maybe it's a different magnet. But the north pole of a magnet here, as the wires come up, they're going to push current one direction, and then as that same wire goes around to the south pole, it's going to move current in the opposite direction. And so it's pushing and pulling in different directions, and the current is going to oscillate. The electrons are going to vibrate, going back and forth and back and forth and back and forth. And the number of oscillations per second, the frequency of the electrical power being produced has to do with how many rotations per minute that the armature is making between the magnets. Okay, and then you would see that this side of the current, or this side of the armature, is always attached to this ring, is always brushing this ring, right? which is going to send the power always to this side of the circuit. And this side of the armature is always going to be in contact with this ring, which will always be sending power to this side of the circuit. And so when this is pushing, electrons will be going this way. When this is pulling, electrons will be going this way. So the AC current oscillates. And here's a graph of that showing the different positions of the coil and what the voltaic potential is doing. So here we would have a maximum forward current, and then we would actually have a split second with no current, and then it starts to go the other way, maximum reverse current, and then a split second of no current again. So this sine wave shape is what we get from AC current. And if you were to hook up an oscilloscope to an AC power supply, you would see it generate those kinds of images there for you. So AC power is a push-pull back and forth. DC power, on the other hand, is generated basically exactly the same, only the difference being that the halves of the circuit get to switch which side of the armature they're touching. So here we have this armature spinning between the different poles of a magnet, and as this wire is in contact with this half of the ring, which brings it to this side of the circuit, notice that it's always by the north pole. So it's going to be creating a north pole influenced circuit over here. And then when the wire spins to the other side in a AC generator, it would still be connected to the same side of the circuit. But here it's connected now to this ring, which goes to this side of the circuit. So this, what's called a split ring commutator, this thing keeps the power from bouncing back and forth. It pushes only in one direction, and then the next side pushes only in that direction. And so you can see that instead of getting a sine wave, we get like a bouncy ball, where the voltage reaches a maximum and then decreases and then goes back on the same side to the maximum. So it bounces only in one direction as opposed to sine waving on both sides of the circuit. Okay, you see the difference? We'll talk about it more in class if you have any questions. Now we're going to show you a couple of electronic components, circuit components. The first one is an inductor, and it uses the relationship between electric fields and magnetic fields to cause a slowdown of current. A little bit of a tricky concept, but I think you'll be able to understand. When a magnetic field creates an electric current, that electric current then creates its own magnetic field as well. And we got to that last lecture where you have the two rings and an electric field in one creates a changing magnetic field, which in the next ring creates an electric current, which creates its own magnetic field. That's why the two wires tended to bounce out from each other a little bit. We talked about a repelling force between two wires where one is being induced by the other. Now we're going to take that same concept of resistance and magnetic interference, and we're going to apply it now to an electrical component. And these components are very small electromagnets. It's a wire that has been wrapped into a coil. It may or may not have a ferromagnetic core through it. And the current of the circuit causes a magnetic field which induces in that same wire a backwards current, just a little slight one. And so what it does is it kind of says, hey, whoa, let's not change. It resists current change. So when a current is flowing at a particular rate at a certain number of amps, the inductor doesn't really have a whole lot to do with that. But when the current starts to drop off, it's going to resist the change in current. It's going to say, hey, no, let's keep going. Or if the current peaks, it's going to say, no, don't peak, slow down a little bit. And so it resists change of current. It stabilizes the current. You'll see this mostly when you turn a circuit on or when you turn a circuit off. You may notice that some devices take just a split second, a little bit around a second to get going. You turn on a device and it comes up and then it's working. That's the inductor slowing down the increase in current. Or if you turn a device off, you may notice that you hit the button to turn it off and it dies over the a measurable amount of time. That's an inductor resisting the drop-off of current. So they don't force a current to keep going when there isn't any more current, but they slow down the change of a current. So they're used to stabilize current flow and to resist little wobbles in the amount of current flow going through a circuit. Okay, and so the symbol for them is a circle, because it's a little coil, right? And the phenomenon we call self-induction, where this coil can create its own current in reverse and stabilize the flow by resisting change. And then we call that unit an inductor. And this is the symbol in a diagram. It's just a coil. Let me show you some allied images here. There you go. So in this coil of wire, we pass a major magnetic field through it, and the magnetic field causes a current to happen. And we do something with that electrical current. But that current in itself creates a resisting magnetic field, which creates a counteracting current in the same ring. So it slows down changes of current, okay? And there's just another diagram for this. An electron flow from a source down a wire causes a magnetic field which creates a reverse induced current. This is self-induction, okay? And that's what happens in those inductors, excuse me. Okay, transformers, another electronic device you should be familiar with. This is not the talking robots from space, right? These are electrical components that use two insulated wires wrapped around a common ferromagnetic core to step up or step down voltage. So one coil is going to create a magnetic field and cause that ferromagnetic rod to become a magnet, and then that magnetic field will then cause a current in the other coil of wire wrapped around it. We talked about these in physical science. It's been a while though. Let me show you some pictures in just a moment to help you refresh your memory. But it's a magnet with two sets of wires on it. And depending on how you wrap them, you can either create a higher voltage or a higher current, or a lower voltage and lower current. And that has to do with the ratio of the wraps on one side of the transformer to the other. So if you wrap one side of the transformer with 4 wraps and then the other side of the transformer with 2 wraps, you would never do it with so few, but the ratio is 1 to 2, right? And so voltage applied to the side that has 2 wraps would create half the voltage potential on the other side of the circuit. Voltage applied to the side that has 2 wraps would cause the 4 wrap side to have twice the voltage potential on the other side. So the ratio of voltage potential to the number of wraps is equivalent on a transformer. It also works for current. The number of wraps on either side also it has the same ratio as the resulting current. So transformers jump up or jump down voltage potentials and current. We use them mostly in large commercial applications for saying this part of a factory needs more voltage. This part of a factory doesn't need as much, so there's a transformer in the power supply. Or in your own home, some appliances require 220 volts and some only require 110. So we'll put a transformer in the circuit, and that plug now has 220 volts of power. Also, the power company will bring very high voltage lines to your home, and then we use a step-down transformer to bring less power into your home because you don't need thousands and thousands of volts of power. So these transformers step up or step down voltage potentials by using differing numbers of wraps of wire around a common ferromagnetic core. This is what a transformer looks like. It again is a common ferromagnetic core, usually a square like this, and then one side of the transformer is wrapped in a certain number of wire turns, and the other side of the transformer is wrapped in a different number of wire turns. So here we would have a power source, and this side has 1, 2, 3, 4, 5 wraps, and then this goes to our load, to the other thing we want to be able to do with this voltage. And this has 1, 2, 3, 4, 5, 6, 7, 8, 9 wraps. So this side would have almost twice the voltage and current as this side. And so we've we've stepped up our voltage potential by having two different wraps of wire around a common core. So what's happening here again is an electromagnetic field is being created by the coils of wire around this core, turns this whole thing into a magnet, and then that magnetic field influences these wires to create a current going out the other side. Okay, here's the symbol for it, showing one side of the circuit, and then this represents kind of the magnetic core, and then this is the other side of the circuit. So it looks like an inductor and an inductor separated by a double line. And that's kind of what it is. It's an inductor and an inductor, but they share the core. All right? Those are the two electrical components for this chapter. Now, 22C has lots to do with analyzing the different kinds of circuits. We're going to skip that at this point, and we're going to move right into the last little conversation in chapter 22, which is about electromagnetic waves and the speed of light. Electricity and magnetism are interrelated phenomenon, and that's why we study them together. They influence each other, they control each other, and they actually radiate together through space. So electromagnetic radiation is the only kind of wave that can propagate without a medium. Sound waves, mechanical waves, anything like that needs some kind of medium to shake. And electromagnetic radiation is the only kind of radiation that doesn't need a medium. It propagates through a vacuum, and that's what makes it special. So when it propagates through a vacuum, the electric side and the magnetic side are propagating each other. They're causing each other. And this may be why it gets to go through a vacuum without a medium, is because it causes itself. So as a changing magnetic field rises, it's causing a changing electric field to rise, and then they will die out together and then cause each other on the other side of the axis. It's really cool. So they propagate 90 degrees to each other. A magnetic wave may be propagating this way, and an electric wave will be propagating this way, and they propagate together. And see if I can make my fingers do this so that they look like this going towards you. Pretty cool. This was described by Maxwell. He was the physicist who did this. He was a student of Faraday. Faraday did a lot of the equations that we just talked about in the last lecture. Maxwell is responsible for this kind of stuff, and they helped us really understand the nature of electromagnetic radiation. So electromagnetic waves travel as two linked waves at 90 degrees to each other. What does that look like? I'm glad you asked. It looks like this. So the wavelength for the electric and the magnetic fields will be the same. The peaks are aligned. The points of neutrality, the median line, is aligned. The troughs will be aligned. But the magnetic field will be operating like this, and the electric field will be operating like this. So they travel through space as linked waves. It's freaky cool stuff. And this is what allows it to propagate through a vacuum. All right, so that's an electromagnetic wave, different than anything else out there. God is so creative, isn't he? And our last conversation has to do with the speed of light in the vacuum. How fast do those electromagnetic waves travel? In the vacuum of space, or the nearly perfect vacuum of space, light travels at an astoundingly fast speed. 3.00 times 10 to the 8th meters per second. Okay, so that's a 3 followed by 8 zeros. That would be 300 million meters per second. 300 million meters per second. Divide that by 10 to the 4th, and we're down to 30,000 kilometers a second. And so that's pretty stinking fast. That's ridiculously fast. That's approximately, I think if I'm rethinking correctly, that's about a lap and a half around the globe every second. So that's ridiculous. Light travels crazy fast. And yet you think about how far away we are from some of the things in the solar system. We're, 9 light minutes from the sun. We're a couple of light seconds from the moon. But then there are probes that we have sent out into the far reaches of the solar system that it takes, hours to get back to get signals back to us. And so, or sometimes I think even days now, we've sent our little sensors out quite a ways, and that's only in our solar system. Other solar systems, other stars are light years away. Other galaxies, light centuries away. Some things are billions of light years away. And so the distances in God's universe are just, they break your brain when you start to think about it. But what we're getting at here is the speed of light and how it changes in various media. So that's the speed of light in a vacuum. As light starts to propagate through a medium like air or water, it slows down. Now, it never becomes slow, right? You're never going to slow light down to the point where you're like, and there goes light. Yeah, no, not going to happen. But it does slow down in a medium, and it has to do with two properties of the medium. One has to do with how easily electricity can pass through the medium, and one has to do with how easily magnetic fields can pass through the medium, because light is both. Electromagnetic radiation is both electricity and magnetism. So we have to take into account the way that these two traits or characteristics of a medium impact the speed of electromagnetic radiation. So the velocity of electromagnetic radiation in a particular medium has to do with the reciprocal of the square root of mu times epsilon. Epsilon is electric permittivity. How easily do electric fields move through this medium? And then the exact same question with magnetic fields and mu. So epsilon is the Greek letter E. You can think about that for electricity. Mu is the Greek letter M, so magnetism. It helps you think about that way. So the square root of the product of mu times epsilon, and then that turns into a reciprocal. 1 divided by that gives you the velocity of electromagnetic radiation in a medium. All right, there you go. That is all she wrote, folks. We'll talk about it again tomorrow. Let me know if you have any questions. God bless you. Have a wonderful day.